Hello and welcome back. So today I'm going to start on a new unit, that is unit 3, that is 3D graphics. Okay, let's start. So 3D graphics, the three-dimensional transformations are extensions of two-dimensional transformations. So first of all, I'm going to discuss on 3D transformations. In 2D, two coordinates are used, that is x and y, whereas in 3D, we use three coordinates, that is x, y, and z. So 3D geometry, the orientation of a 3D coordinate system is of two types, that is right-handed system and left-handed system. So in the right-handed system, thumb of right hand points to positive z direction and left-handed system thumb points to negative 2 directions. Okay. Now we'll see only right-handed system. Okay, let's see how a right-handed system is there. So this is a figure showing the right-handed orientation of the cube. Okay. Here we have coordinates of corners A, B, C, D of the cube, where point A is on X, Y, Z plane and point B is on X, Y, 0, point C on 0, Y, 0 and point D on 0, Y, Z. Okay. This is how a cube can be shown in 3D right-handed system. Now we'll go on to the basic transformations, that is 3D transformation. So we have seen 5 transformation in 2D, right? That is translation, scaling, rotation, reflection, and shearing. The same transformations we are being studying in 3D transformations also. So first we are moving on to translation. So it is the movement of an object from one position to another position. So translation is done using translation vectors. So there are 3 vectors in 3D instead of 2. These vectors are in X, Y, and Z direction. So we'll see the equations. If a P is a point having coordinates in 3 directions, X, Y, Z is translated. Then after translation, its coordinates will be X1, Y1, Z1 after translation. So this is how we have done in 2D also. Okay. So Tx, Ty, Tz are translation vectors in X, Y, and Z directions respectively. Okay. So we have X1 is equal to X plus Tx, the equation for translation. Y1 is equal to Y plus Ty and Z1 is equal to Z plus Tz. Now this is how we can translate a point X, Y, Z from X1, Y1, Z1. Okay, and this is how a cube is being translated. So three-dimensional transformations are performed by transforming each vertex of the object. So suppose we say that if an object have 5 corners, then the translation will be accomplished by translating all 5 points to a new location. So here the first figure shows the translation of a point and the second figure shows the translation of a cube. Okay. Now this is the matrix for translation. See 1, 0, 0 will be having 4 into 4 by 4 matrix here because it is a 3D representation of translation. Okay. So we have 1, 0, 0 Tx, 0, 1, 0 Ty, 0, 0, 1 Tz and 0, 0, 0, 1. Okay, we have 3 translation vectors Tx, Ty and Tz and the fourth coordinate will be always 1. So this is how we are being translating when it comes to a point translation. Okay. Now our next topic is scaling. So scaling is used to change the size of an object. The size can be increased or decreased, same as we have seen in 2D transformation or 2D scaling. So Sx means scaling factor in x direction, Sy means scaling factor in y direction and Sz means scaling factor in z direction. So the equations will be x1 equal to x dash is equal to x into Sx, y dash is equal to y into sy, and z dash is equal to z into sz. So here is the matrix for scaling. See, suppose we can say that what we have said in 2D also. If all scaling factors Sx equal to Sy equal to Sz, then scaling is called as uniform. If scaling is done with different scaling vectors, it is called as differential scaling. So this is the matrix for scaling. Sx 0, 0, 0, 0, Sy 0, 0, 0, 0, Sz 0, and 0, 0, 0, 1. Now we have the next transformation, that is a rotation. So it is moving of an object about an angle. Okay, moving can be anti-clockwise or clockwise. So here we are considering only clockwise directions. For 2D, we describe the angle of rotation, but for a 3D angle of rotation, an axis of rotation are required. So we have three axes, right? The axis can be either x or y or z. So here, along with the angle of rotation, we consider also the axis of rotation. So first is the rotation about z axis. This is a rotation about z axis in clockwise direction. Okay. Then this is the equation for rotation about z axis. So x1 equal to x cos theta minus y sin theta. Y1 is equal to x sin theta plus y cos theta, and z dash is equal to z because we are rotating it about z axis. So the z axis remains the same. Then the matrix for rotation about z axis. Cos theta minus sin theta 0, 0, sin theta cos theta 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay. Now we'll have the rotation about x-axis. Okay. So this is the clockwise rotation about x-axis. Now we have, since it is rotation about x-axis remains the same. So x1 equal to x, y1 equal to y cos theta minus z sin theta, and z1 is equal to y sin theta plus z cos theta. And this is the matrix for rotation about x-axis. So we have 1, 0, 0, 0, 0 cos theta minus sin theta 0, 0 sin theta cos theta 0, and 0, 0, 0, 1. Then rotation about y-axis. This is the figure which shows the rotation about y-axis. Okay. Here I have represented a figure for more clarification. So I have rotated the figure from y-axis to the opposite, in the clockwise direction. Okay. Now x1 is equal to z sin theta plus x cos theta. Y1 is equal to y because we are rotating about y-axis. So y-axis remains the same. And z1 is equal to z cos theta minus x sin theta. This is the matrix for rotation about y-axis. We have cos theta 0, sin theta 0, 0, 1, 0, 0, minus sin theta 0, cos theta 0, 0, 0, 0, 1. See, all these formulas, we have been, all these matrix representations and all these formulas for all these transformations are the same as of 2D. Only the difference is that the coordinates will be, there we have represented using 2 coordinates. Here we are representing using 3 coordinates. Our next transformation is reflection. So it is also called a mirror image of an object. For this, reflection axis and reflection of plane is selected. Okay. Along with the axis, we are selecting the plane also. Then reflection is 180 degree above the given axis. And for reflection, plane is selected as XY, XZ or YZ plane. Now we'll see matrix for reflection about XY plane. This is how we are representing reflection about XY plane. Then the matrix for reflection about YZ plane. Okay, this is how we are representing the matrix for reflection about YZ plane. Then matrix for reflection about ZX plane. Okay, this is the matrix for reflection about ZX. Our next transformation is shearing. It is a change in shape of the object. It is also called as deformation. Okay, we are changing the shape of the object. In 2D, we have shown a unit cube changing its shape along x-axis and along y-axis. So 3D shear can occur in 3 directions. Okay. So this is the matrix for performing shearing. Okay. We have given A and B as a coordinate. So A and B are being substituted by whatever value we have been given. This is the matrix for shearing. Thank you so much. I hope today's episode was very clear. It's only the same which we have studied in 2D transformations, only that the coordinate system is different for 3D.